Section 1.7 on page 56 talks about linear independence, a big deal. Linear independence or linearly dependent. So, an indexed set of vectors v1 through v sub p belong to R sub n is said to be linearly independent if you take the weights x1 times v1 plus x2 times v2 all the way to x sub p. That's like c1 v1 c2 v2. You set them equal to the zero vector, has the only trivial solution. And in case you don't know what the trivial solution is, the trivial solution will be x1 equal x2 equal x3 equal x sub p, and all of these are zero. That's called the trivial solution. The idea is matrix A times vector x equals 0 is called a homogeneous equation because it equals 0. X equals 0 is trivial. If you let x equals 0, well, that's going to always be 0. You're looking at if x doesn't equal 0, what must A equal so that when you do the product, you get a 0. So this is always a giveaway. When they say the only solution is the trivial solution, they're saying if you take this matrix and write it as A x equal to 0, if you can only get the x's to be exactly 0, that one trivial solution, then those are linearly independent. And if not all of them are 0, if one of the x's is not 0, you say those are linearly dependent. That's simple. So I'm looking at page 61 and I'm starting with a problem. It says determine if the vectors are linearly independent. Well, a couple of ways I could do that. The best way, well, by definition, so I'm really supposed to take x1 times v sub 1, assuming this is v1, plus x2 times v2, assume that's v2. I put the error in the wrong place. Plus x3 times v sub 3, assume that's v sub 3. And what do? You set that equal to 0. Meaning, if I take x1, x2, x3, and I add those, isn't that the same as pretty much saying 0, 0, 2, 0, 5, negative 8, and negative 3, 4, 1 times x1, x2, x3 equals 0? So aren't you solving really this system of equations? Right? Assume that's x1, x2, and x3. You're trying to find those solutions. And what if I told you I worked this out and what I got was a 2, negative 8, 1, and 0. I got a 0, 5, 4, and 0. And I got a 0, 0, negative 3, and 0. What would you say? Do you see that 3x3 equals 0? If you put that in there, doesn't that mean 5x2 equals 0, which means x2 equals 0? And if you put 0 there and 0 there, if 2x1 equals 0, doesn't that mean the only solution here is the trivial case? Which means what? Those are linearly independent. So again, if I really wanted to write this out, this really writes out as x1 times 0, 0, 2. So we were talking about that last time and how this is how they're going to write most of the definitions. And you need to know what that means. And let's make sure we see it clearly because this is something we're going to use all throughout. And this becomes 0, 0, 2x1. Again, in case you want to see it, this becomes 0, 5x2, negative 8x3, and this by definition, this is x1 times 0, 0, 2 plus x2 times 0, 5, negative 8 plus x3 times negative 3, 4, 1, and you're going to set that equal to the 0, 0, 0 vector. The 0 vector, I should say. And doesn't that mean you're really looking at 0, 0, 2x1 plus 0, 5x2 minus 8x2 plus negative 3x3 plus 4x3 plus x3 equal 0, 0, 0. And we know that we could add those by saying this is the column for x1, this is the column for x2, and this is the column for x3. And we could use the augmented matrix to solve the equation. You really could skip all of this. You really don't need to write that, but you need to understand that's what you're doing. Because the definitions are not going to really stop using that notation. Just get it out of the way. And how about this problem right here? Well, this is very simple. You're trying to know if it's linearly independent. Linearly independent is when one of those is not a multiple of the other. So simply, if I multiply, you notice there's only two of them. If I take 2, call this v sub 1, call this v sub 2. So notice 2v sub 1, if I multiply this by 2, that will be a negative 2, that will be 8, does not equal v sub 2, so therefore they're linearly independent. That's simple. Or you are welcome to try x1 times negative 1. Let me write it out again. I'm not going to do that after this. You are welcome to write it out. You could say x1 v1 plus x2 v sub 2 equal the 0 vector, or x1 times negative 1, 4 plus x2 times negative 2, 8 equal 0, 0, or negative x1 for x1 plus negative 2x2, 8x2 equaling 0, 0, and you come up with the augmented matrix. And the augmented matrix will be negative 1, 4, negative 2, 8, 0, 0. I could have jumped straight from this to this. And if I multiply row 1 by a 4 added to the second row, I'll get negative 1, negative 2, 0, negative 1. That makes this, I'm sorry, negative 4, 8. That makes this, what did I say? Multiply by 4 added to this 4. Negative something, that's a negative 8, there it is. I was getting 0, 0. I'm like, wait a minute, what just happened? I thought this didn't work. Multiply this by negative 4, so that's negative 16. And doesn't that mean that x2 equals 0? And if you put it in there, x1 equals 0. Therefore, linearly independent. If the only solution is the trivial solution, which is all of them are zeros, then pretty much you're done. Now, and here's the official definition. The columns of matrix A, recall that the columns of matrix A, if you look at a matrix, do remember that the columns are actually those vectors. The columns of matrix A are linearly independent if and only if, when you set this equal to 0, you has the only trivial solution. What's the trivial solution? If they're all 0. So again, what we just mentioned, they're going to give you that in so many different forms, and it's not going to change. That's very efficient. Determine if the columns of the matrix form a linearly independent set. Again, they could have gave you that like they did with number 2 and 4. Now they're giving you that in a vector. So basically what they're saying, if this is matrix A, right? Set AX equal to 0 and solve. If the only solution would be x1, x2, x3 equals 0, then you're in good shape. You're done. Those are linearly independent. And if you get any other solution, so an infinite amount of solutions or any solution other than the zeros, will indicate that this is infinitely many solutions, linearly dependent. So if I throw the augmented matrix, if I make this -4, 0, 1, and 5, you know what? And 5, let me make it, there we go. So something to get used to. -3, -1, 0, and 4. 0, 4, 3, and 6. And if I set this equal to the 0 and solve and see the weights, if I actually work this out, this is what I'll get. I'll get a 1, 0, 3, 0, 0, -1, 4, 0, 0, 0, 7, 0, and one of those 0 completely out. Now, if I look at this, remember pivot points. It turns out this is extra. This is not a free case. This is not X. This is X1. This is X1. This is X2. This is X3. There are only 3 of those. So I'm looking at the columns, right? There are 3 pivots. What's the solution? Isn't the solution here? The only solution is that x1 equal x2 equal x3, and that is 0. Therefore, the columns, and the column stands for the vectors, are linearly independent. Again, if I set 7 times x3 equals 0, I'll get 7, 3 equals 0. Plug it in, that makes this a 0. Plug it in, that makes that equals 0. And that's something we're going to do a lot. Again, you want to get that out of the way. So the difference between number 6 and number 8. Number 6, they gave us vectors with 4 components, but each one of those stands for one variable, x1, x2, x3. When I look at number 8, automatically, if I'm going to set it equal, I don't need to do the work. 1, -3, 0, -3, 7, 1, 3, -1, -4, -2, 2, 3, and 0, 0, 0. Curiosity. I have x1, x2, x3, and x4. How many pivots can I get at most? At most, I can get 3 pivots, but I have 4 variables, which indicate what? Which indicates that x sub 4 is free. And doesn't that mean you have an infinite amount of solutions? Therefore, x1 equals 0, x2 equals 0, x3 equals 0, x4 equals 0 is not the case. Linearly dependent. I don't have to do any work. So make sure you see the difference between this problem and this problem. And they're nothing alike. So no need to do the work. And that's the part I've been mentioning. Make sure you understand the theorems. Make sure you understand the definition. Make sure you don't get into this, I want to solve. There isn't much to solve, really. There's a lot of work. There's a lot of theorems you need to use, but you're not going to be doing a lot of work. Do you understand what the theorem is saying? That's really what counts. And here we go. The idea doesn't change now. They're going to start elaborating on prior sections. For number 9 and 10. Well, for what values of h is V3, this is V3, in the span? And remember what we said is in the span. Any vector is in the span if it's a multiple of those two. Basically what they're saying, take x1 times v1 plus x2 times v2 and set it equal to v3. They're saying for what values of h is, and what you want a solution. So in part A, we're really looking at 1, -5, -3, -2, 10, and a 6, and a 2, -9, and an H. Now what I'm going to do the magic. Multiply row 1 by 5, add it to row 2. Multiply row 1 by 3, add it to row 3. Well, once you do that, you'll notice, add row 1 by 5 and add it to row 2. What happens? 5, 0, 0, and 10 minus, that's a 1. If you multiply by a 3, row 1, that's a 0, 6, that's a 0, and that is H plus 6. But before I even reach that, I notice we have a problem. What's that? I notice that this is saying x2 times 0 equal 1, but 0 cannot equal 1. There's no solution. If there's no solution, what does that mean? If there's no solution, that means the original assumption is not true. Therefore, V sub 3 is, for what values of H is V3? V3 cannot be in the span. V3 cannot be in the span for any value of H. For any H. That's part A. How about part B? B says, for what values of H is V1, V2, V3 linearly dependent? What does that mean? Okay, well, let's look at this. The idea was I'm going to take x1 times v1 plus x2 times v2 plus x3 times v3. It's really almost like this, equal to 0, and see if the only solution is x1 equal x2 equal x3, which is 0, that's linearly independent. Otherwise, it's linearly dependent. Meaning what? If I write those vectors out, I'm looking at 1, -5, -3, -2, 10, 6, 2, -9, and H. And if I make that 0, 0, 0, and if I do my magic, again, multiply row 1 by 5, add it to row 2, multiply row 1 by 3, add it to row 3, the bottom line, if I do all of that work, I will get a 1, -2, 2, and a 0. I'll get 0, 0, 1, and a 0. And I'll get 0, 0, H plus 6 and a 0. And if I multiply this row by -H plus 6 and add it to the last row, do you see that those 0 out? Right? So if those 0 out, doesn't that mean that x3 is free for any value of H? And therefore, I didn't get the trivial solution. Therefore, those 3 vectors are linearly dependent for any value of H. And this is how you write for any or for all values of H. Upside down, A is for all. So the following 2 theorems are reiterating what we already know. A set of 2 vectors is linearly independent if at least one of the vectors is a multiple of the other. We know that already. And if a set contains the 0 vector, then it is linearly dependent. I'll show you that right there on number 20. So here they say, determine by inspection whether the vectors in 15 through 20 are linearly independent. Well, let's look at number 16. There's only 2 vectors. Well, how do you get from this to this? Multiply or divide 6 by 3 halves. If you multiply by 3 halves, 2 divides 4, 2 times 3, that's a 6. Does that work on all of them? Divide this by 2, that's -1, -3. So, yep, there it is. So this is linearly dependent. How is that? Well, if you call this, again, I'm going to refer to the first, always V1, V2 in that order. I'm going to say V2 is 3/2 V1. One of them is multiple of the other. We have a theorem for that now, but we could use common sense, assuming me and you have the same common sense. And do you see what's wrong with this? This is automatically linearly dependent. Why is that? Well, we only have 2 entries and 4 vectors. Doesn't that mean we're going to have at least 2 free variables? If you write this as a matrix, say that's x1, x2, x3, x4, you can only have at most 2 pivots, which means 2 of the rows are 0. And this is automatically, by that theorem, this is theorem 9, linearly dependent. Why is that? Well, it's very easy. Take 0 times v1 plus 0 times v2. Wouldn't you get v3? They are multiples of each other. So it's more understanding than doing. A lot of that coming your way. Section 1.7, page 61. Again, do numbers 1 through 19